Hello class, welcome to today's lesson. We have been looking at differentiation of a function and today we'll continue with it. So before the lesson will end today, I expect that you should be able to know how to find the derivative of a polynomial to the degree of any form accurately. Then secondly, you should be able to differentiate the natural exponential function of the form f of s equal to e exponent ks, where k is constant. Then you should be able to identify that if a function f of s is equal to a exponent x is differentiable at s equal to 0, then it is differentiable everywhere in its domain. This will be a very interesting lesson, so please I indulge you to pay attention as we proceed. So in our previous lesson, we look at how to find the limit at a point. That's the limit as x approaches a particular point of a function. So I want us to discuss how to solve the limit as s approaches 2 of x squared minus 4 all over x over minus 2. So we said that when we meet this problem, first the form of the problem need to be determined. And how do we determine the form? We determine the form by substituting the limiting point into the function and see the form that it takes. So we say that the limit of s squared minus 4 all over s minus 2 as s approaches 2. So let's substitute 2 there. So we get 2 squared minus 4 all over 2 minus 2. And that will give us 4 minus 4 over 2 minus 2 is 0, and that will give us 0 over 0, and we say that this is undeterminate form. So having known that the function is undeterminate form, what do we learn? We said that we have to know how to solve it algebraically. So let's proceed as we solve this algebraically. So we said that first we need to find how to expand the function at the top. So if we have the limit of x squared minus 4 all over x minus 2 as s approaches 2, we can write this as the limit of x plus 2, x minus 2, since this is difference of 2 squared, over x minus 2 as s approaches 2. So we can say that this s minus 2 can divide this s minus 2. So we just be left with the limit of x plus 2 as s approaches 2. And that will give us 2 plus 2, and that is 4. So if you are able to solve this, kudos to you, and it will help us in today's lesson. That's why I want us to go over it again. Also, we said that from the definition of derivative, we said that the derivative of a function is given as a function f of s is given as f prime of x is equal to the limit of f of x plus h minus f of x all over h as h approaches 0. And how do we use this? So for example, if we have a function f of s equal to s squared, the derivative of this function, using the definition of derivative, we say that f prime of x will be equal to the limit of f of x plus h minus f of x all over h as h approaches 0. So f of x is equal to x squared, remember that? So we say f of x plus h will be equal to x plus h squared. So we can expand this. We have s plus h, s plus h. So this will be x squared plus 2sh plus h squared. So in substituting that, we can say that f prime of x will be equal to the limit of, so f of x plus h is x square plus 2sh plus h square, then minus f of s, which is what, x square, all over h as h approaches what, 0. So we have, so you can see that this s square can subtract that, so we left with the limit of 2sh plus h square all over h as h approaches 0. So finally, we can solve this as that. You see that h is common, so we bring it out. So we have the limit of h bracket 2x plus h all over what, h as h approaches 0.
Let's continue.
So from here, we can say f prime of x is equal to the limit. So this h divides that, so we have 2x plus h as h approaches 0. So when we reach here, we can just substitute the 0. So we have 2x. So f prime of x is equal to 2x. So we say that if f of x is equal to x squared, then f prime of x will be equal to 2x. So having been able to remember how to find the limit of a function at a particular point and how to be able to use the definition of a derivative of a function, we will now look at how to find the derivative of a constant function. So we say that if we have a function f of s equal to c, where c is what? Constant. So we say constant, say 1, 2, negative 3, 7 exponent 9 among others. If derivative from the definition of a derivative as f prime of s is equal to the limit of f of s plus h minus f of x all over h as h approaches 0. So we are going to use this definition to find the derivative of the function. So remember, the function f of s is just a constant, say c. So we can say that f of s plus h will just be c, because we don't have any variable attached to the c, right? So f prime of x from the definition of derivative will be equal to the limit of, so s plus h is just c minus f of s, which is also c, all over h as h approaches 0. So this is just the limit of 0 over h as h approaches 0. So 0 over h is just 0. The limit of 0 as h approaches 0 is just equal to 0. So we can therefore conclude that the derivative of any constant function say c, that's d over dx of any constant function is equal to 0. That when we are finding the derivative of any constant function is just 0, and we are able to get that from the definition of derivative. Now, so let's find the derivative of the following functions. So let's say y is equal to negative 7, y is equal to 22, and y is equal to 567 exponent 1000. So what will be the derivative? From here, since y is equal to negative 77, it's just a constant function. Your guess is as good as mine. The derivative dy over ds is equal to 0. The second one, also, the derivative of dy over ds is equal to what? 0. Then the third one, since there is no variable attached to that, we can term this as a constant function. So we say that the derivative dy over ds is also equal to 0. Okay, so from the definition of derivative, you see that when we find the derivative of a function f of x squared, we had f of x squared, we had 2x. So keep that in your mind. So now let's continue to find the derivative of the function y equal to s cubed using the definition of derivative. Remember, from the definition of derivative, we said that y prime in this case will be equal to, okay, so if y is equal to f of x, which is equal to x cubed, then our y prime will be equal to f of x plus h minus f of x all over h. That's, sorry, the limit of that as h approaches 0. So from here, we know that our function is s cubed. So if we want to find f of s plus h, that will be equal to x plus h all cubed. So this can be x plus h squared times x plus h. So when we expand this function, that's s plus h, we'll get x squared plus 2sh plus h squared. Remember when we expanded x plus h squared, then times our x plus h. This, when you expand it very well, you end up getting x cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, so now we know that f of x plus h is giving us this, and f of x is just s cubed. So let's substitute that into our our derivative function. Then we can say our y prime, or the differential of y, will be equal to the limit of x cubed, which is f of x plus h. So x cubed plus 3x squared h plus 3xh squared plus h cubed, then minus x cubed all over h as h approaches 0. So x cubed, we can subtract that will give us 0. So we have the limit of 3x squared h plus 3xh squared plus h cubed all over h as h approaches 0. So this will be the limit as h approaches 0. So you see that h is common to all of them, so it's a common factor, we can factor that out. So h out, we have 3x squared plus 3sh plus h all over h. So this h plus h squared. So this can divide this, so we have the limit as h approaches 0 of 3x squared plus 3xh plus h squared. So we just substitute the 0 to get our differential. So we substitute to get 3s squared, then plus 3s times 0, then plus 0 squared. So this is 0, that's 0. What will be left with is just 3x squared. So we say our y prime of x is equal to 3x squared. So you realize that when we're having y is equal to x squared, our dy over dx was just 2x using the definition of derivative. And when y was equal to x cubed, our dy over dx, what did we get? We had 3x squared. So what is happening? You see that there is a pattern happening. Look at this. So we have s squared, and these two multiply the function. So, and what happened? We subtract 1 from the exponent. So look at it. So we have, when we have x squared to differentiate this function, we say that the 2 will multiply x. Is following a pattern. So we say 2x, then minus 1. We subtract 1 from the exponent, and that gives us 2x. The same way, this one, when we're having y equal to x cubed, dy over dx will just be equal to, so we drop the exponent to multiply the function, so 3x cubed, then we subtract 1 from the exponent, and that resulted into 3x squared as what we got when we're using the definition of derivative. So we can therefore say that if we have a function y is equal to s exponent 4 dy over ds, please can you get the answer? So the answer will be 4x cubed. That's great. You were able to do that excellently. So you just subtract 1, you just let the exponent multiply the function and subtract 1 from the exponent. So can you do this for me? Okay. So our dy over dx will be equal to 5x exponent 4. That's excellent. So we can conclude that if we have a general function f of x equal to x exponent n, when n is constant, its derivative, that's d over dx of x exponent n, we said that you just drop the exponent to multiply the function, so we have n x exponent n, then we subtract 1 from the exponent. So this is known as the power rule, actually. So the power rule says that the differential of the function d over dx, that's x exponent n, is just nx n minus 1. So for example, we can use the power rule to find the derivative of any function having an exponent. So if we have y is equal to, given that y is equal to the square root of x, we should find dy over dx. So if y is equal to the square root of x, we can say y will be equal to s exponent half. Remember, the square root of every function is that function exponent half. Then using the power rule, our dy over dx will be equal to half. So we drop the exponent to multiply the function. Then we subtract 1 from the exponent using the power rule. So this will give us half s exponent negative half. So our dy over dx will be equal to, so we can rewrite this function as 1 over 2 s exponent half using indices. So this will be equal to 1 over 2 the square root of x. Remember, we said that the square root of any function is that function exponent half. So using the power rule, we can say the differential of y is equal to root of s is just 1 over 2 root of x. So let's look at our second example. So if we have a function f of s equal to 1 over x cubed, and we are asked to find the derivative, that's f prime of x. So using the power rule, remember f of x is equal to 1 over s exponent 3. We can rewrite this function as f of s equal to x exponent negative 3 using indices, the properties of indices. So our f prime of x from power rule is that we drop the exponent, so we have negative 3, then we repeat it and subtract 1 from the exponent. So that will be equal to negative 3 s exponent negative 4. So we can rewrite it as negative 3 over s exponent 4. So apart from the power rule, we also have a constant multiply rule. We have sum rule and difference rule of differentiation. And we'll go through that. That will all guide us to be able to find the derivative of any polynomial function. So we say that the constant multiply rule states that if we have a function y equal to ax exponent n, then the derivative of this function, that's dy over dx, will just be equal to a n s exponent n minus 1. So this involves the power rule as well. So you just drop the exponent to multiply the constant multiplying the function, repeat the function and subtract 1 from the exponent, just for the power rule. So for instance, if we have y equal to 7x exponent 2, then our dy over dx will be equal to 2 times 7s exponent 2 minus 1, and that will give us 14x. 2 minus 1 is just 1, and that will give us 14x. So the sum rule also states that if we have a function f of x equal to g of x plus h of x, then the derivative of this function, that's d over dx of g of x plus h of x, is equal to d over dx of g of x plus d over dx of h of x. This simply means that to differentiate any two functions adding, you differentiate them term by term. So it's as simple as the same thing applies to the difference rule too. If we have a function y is equal to maybe f of x minus g of x, then the derivative of this function, that's d over dx of f of x minus g of x, will just be equal to d over dx of f of x minus d over dx of g of x. So for instance, we have a function y is equal to 2 exponent 6 minus 3 exponent 5 plus 7x squared minus 4x minus 8. And we have to find the derivative of this function. So using all the rules that we look at, power rule, sum rule, difference rule, and the constant multiply rule, we say that dy over dx of this function will just be the differential of the function 2x exponent 6, then minus the differential at 3x exponent 5 plus the differential at 7x squared, then minus the differential of 4x, then minus the differential at 8. So our dy over dx will be equal to, so using the constant multiply rule with the power rule, this multiply this and that will give us 12. So we have 12 x exponent 6, then we subtract 1 from the exponent, so we have 12x exponent 5 minus the same thing here, this multiply that will give us 15, we subtract 1 from the exponent, we get 4, so that will be 15x exponent 4 plus the same thing for this multiply that will give us 14x, when we subtract 1 from 2 is 1, then minus, remember this function, the exponent of this function is 1, and 1 times this 1 will still be, 1 times 4 will still be 4, and when we subtract 1 from the exponent, we'll get s exponent 0, and s exponent 0 is 1. And remember we said the differential of a constant, we looked at it earlier, is just 0. So the differential of the function 2s exponent 6 minus 3 exponent 5 plus 7s squared minus 4s minus 8 is just 12s exponent 5 minus 15s exponent 4 plus 14x minus 4. So let's look at our second example. The second example is to find the graded function of the function y equal to negative 1 all over x exponent 2025 minus 2s exponent 2 square root of x plus s exponent 2024 plus 2026. So if you see this function, you look at it, you think it will be difficult, but combining these rules, we'll be able to differentiate it easily. So remember, y is equal to negative 1 over s exponent 2025 minus 2 root of x plus s exponent 2024, then plus 2026. This is an interesting function, but it will be very easy to solve. So we just rewrite the function again. So our y will be equal to negative 1 times, so we can rewrite this using the laws of indices, s exponent negative 2025, then minus 2, we can rewrite this. Remember we said this will be s exponent half, then plus s exponent 2024, then plus 2026. So now we can differentiate the function. So dy over dx will just be equal to d, the differential of the function. So this will be negative negative 1 times that will be negative s exponent negative 2025, then minus d over ds, the differential 2s exponent half, then plus d over dx of s exponent 2024, then plus d over ds, the differential of 2026. So we are able to combine all the necessary rules to solve this. So our dy over dx will just be equal to, so here we apply the power rule to solve this. So we say this multiply that, so negative 1 multiply negative 2025 s exponent negative 2025, then we subtract 1 from the exponent, then minus this multiply that, so we have 2 times half s exponent half minus 1, then plus drop the exponent 2024 s exponent 2024 minus 1. Then this is just a constant. Remember that the differential will just be 0. So our dy over dx would therefore be equal to 2025. That's negative 1 times negative 2025 will be 2025 s exponent negative 2026. That's negative 2025 minus 1. Then minus 2 times half is 1. So half s exponent half minus 1 will be negative half. So s exponent negative half. Then plus 2024 s exponent 2023. So our dy over dx will be equal to, so we can rewrite this as 2025 over s exponent 2026, then minus 1 over s exponent half, then plus 2024 s exponent 2023. So we can repolish this as dy over dx is equal to 2025 over s exponent 2026 minus 1 over root of x, then plus 2024 s exponent 2023. I hope you get this. So the next thing we'll talk about is the derivative of a natural exponential functions. So natural exponential functions are functions of the form f of x is equal to e exponent kx, where k is constant. So by definition, the number e is a number such that the limit of e exponent h minus 1 over h as h approaches 0 equal to 1. This is very, very important. We could prove this using graphs, but just identify that when the limit of e exponent h minus 1 over h as h approaches 0 is nothing but equal to 1. We are going to use this concept to find the derivative of an exponential function e exponent x using the definition of derivatives. So from the definition of derivative, we said that if we have a function y is f of s, y is equal to f of s, then f prime of x will be equal to the limit as h approaches 0 of f of s plus h minus f of x all over h. So in this case, we'll let our y to be equal to f of x equal to e exponent x. Then our f of x plus h will be equal to e exponent x plus h, which is equal to e exponent x times e exponent h using the laws of indices. So from here we can say our f prime of x is equal to the limit of f of s plus h, and f of s plus h is e exponent s times e exponent h. So we can say this is e exponent x times e exponent h. Then our f of s is e exponent x all over h, the limit where h approaches 0. So you can see e exponent x is common to both terms. So our f prime of x, we can factor that out. We have e exponent x, the limit as h approaches 0 of e exponent h minus 1 all over h. And remember, we said this is what? 1 from the definition. Then our f prime of x is equal to e exponent x. So if we have a function f of x is equal to e exponent x, then the differential of the function, which is dy over dx, will just be equal to e exponent x. So you realize that when we differentiate x, we get 1. So it means that anytime you are differentiating an exponential function, just differentiate the exponent and use it to multiply the function. So we say that you realize in differentiating an exponential function e exponent x, just differentiate the exponent and use the differential of the exponent actually to multiply the function. So we are going to use that idea to find the derivative of any exponential function. For example, find the derivative of the function y is equal to e exponent root x. So we need to first find the derivative of the exponent, then we just use it to multiply the function, and that becomes the derivative of the function. So we let our f of x to be equal to the exponent in this case. So our f of x is equal to x exponent half. We can rewrite that. Then from the power rule, our f prime of x will be half s exponent half minus 1. And our f prime of x will be equal to half s exponent negative half, which we can rewrite as 1 over 2 s exponent half. We can still rewrite this as 1 over 2 roots of x. So now that we know the differential of the exponent, we just use it to multiply the function and say that our dy over dx then will be equal to the differential of the exponent then times the function e exponent root x. So our dy over dx will just be e exponent root x over 2 root x. Okay, so let's look at the second example. It says if y is equal to e exponent negative 2x minus 4x squared, we should find dy over dx, or we should find the derivative. So remember, from the difference rule, the differential of this function will just be the differential of e exponent negative 2x minus the differential of 4x squared. That's we differentiate the function term by term. So our dy over dx will be equal to, so the differential of this, remember we just differentiate the exponent. The differential of negative 2x is negative 2. Then we use it to multiply the function. Then from the constant multiplier rule and the power rule, we use these two to multiply the 4. That becomes 8, and subtract 1 from the exponent. So the differential of this function, or the derivative of this function, is this. So the next thing we talk about is to find the derivative of an exponential function. We are not going to go into detail of it. We just want to find out if the function, the exponential functions are differentiable at the point x is equal to 0. So we say exponential functions are functions of the form f of x is equal to a exponent x, where a is constant. So let's try to find the derivative of these exponential functions using the definition of derivatives. So we can say our dy over dx will be equal to the limit of f of x plus h minus f of x all over h, where h approaches 0. So we can say that y should be equal to f of x, and that will be equal to a exponent x. Then f of x plus h will be equal to a exponent x plus h, which is a exponent x times a exponent h. So we can substitute this into our derivative. dy over dx will be equal to, so the limit where h approaches 0. So f of x plus h is a exponent x times a exponent h minus f of s is a exponent x over h. Okay, so you can see that a exponent s is common to both sides, so we can bring it out. So we say that dy over dx, or f prime of x, is equal to a exponent x, the limit of a exponent h minus 1 over h as h approaches 0. So let's try to find the value of the derivative at the point x equal to 0. So you can say f prime of 0 will be equal to a exponent 0, the limit where h approaches 0 of a exponent h minus 1 over h. A exponent 0 is 1, so we can say f prime of 0 is equal to the limit where h approaches 0 of a exponent h minus 1 over h. So you realize that the limit where h approaches 0 of a exponent h minus 1 over h is f prime of 0. So in place of this is just f prime of 0. Then we can say f prime of x is equal to a exponent x f prime of 0. So our f prime of x will be equal to f prime of 0 a exponent x. So you can realize that at the point x is equal to 0, the function is differentiable. Then we'll use a method or an approach which we'll be looking at later on in this course to find the derivative of such functions. So we can conclude that if the function f of x is equal to a exponent x is differentiable at x is equal to 0, then it is differentiable everywhere in its domain. Okay, so that brings us to the end of today's lesson. Before we finish, or before we go, let's try to summarize everything we have learned. So today we look at how to find the derivative of a constant function. And from the definition of derivative, we found out that the derivative of a constant function is nothing but 0. We also talk about how to find how to use the power rule to find the derivative of polynomials of degrees or having specific degrees. So like if we have x exponent n, we just drop the n or the exponent to multiply the function, then we subtract 1 from the exponent. That's nx exponent n minus 1. We also look at the constant multiplier rule, which says that if we have a constant multiply the function, let the exponent multiply the constant, then you apply the power rule, that by subtracting 1 from the exponent. And also the differential of an exponential function is just e exponent s is just the derivative of the exponent multiplied by the function. And we also look at we're also able to prove that if y is equal to a exponent s is differentiable at S is equal to 0, then it is differentiable everywhere in its domain. So that brings us to the end of today's lesson. So we have some homework problem. Try to pick one and solve so that when we meet in our next lesson, we'll discuss them.